there? All right. Welcome to another day of physical science and chemistry part, which is the most amazing part. Today we're going to be learning about, can you see it up on the board yet? No? Okay. Today we're going to be learning about buoyant forces and some other different types of forces and concepts that are connected to the kinetic molecular theory that we were talking about, learning about before. Okay, so here we're going to talk about fluids, and that's the actual chapter, but we're going to kind of focus on the applications of the kinetic theory. So let's apply the kinetic theory to the concepts of pressure, viscosity, diffusion, and thermal expansion, and let's see how those things all play out. Okay, so tires, right? Tires are filled with gas. What is it that keeps those tires inflated? All right. What keeps them inflated is going to be a whole bunch of tiny little particles bouncing around really fast, making collisions with the sides of the containers and giving it pressure. That's what pressure is, right? So pressure, force exerted per unit area of a surface. It results from the particles hitting the walls of the container. How does pressure change when gas is removed from tires? Think about that. How would my pressure change if gas is removed? Would it increase or decrease? It's going to decrease, right? My pressure should decrease. If I'm pulling away gas, that means there's fewer collisions with the inside of my tire. Therefore, it is going to decrease my pressure. How does the pressure change when a tire is warmed from 25 to 50 degrees Celsius? Don't forget the temperature is a measure of the average kinetic energy, right? And so again, we're kind of talking about how does the kinetic theory tie into all this? If I increase the speed of my molecules, I'm going to increase the number of collisions that are taking place, right? So here's a molecule, bonk, it bunks in every once in a while, bonk, 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 all right, bonk. But if this molecule is heated up, then it's like, wee, and now it's moving faster. So now it's like, bonk, 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 right? It's going to go over and over and over and over again. So pressure is going to increase. When you increase the temperature, increases the pressure of the tires, all right? And this is why your car will behave differently on a cold day than on a warm day. The actual tire inflation can change, okay? And that's why we oftentimes use nitrogen in our tires instead of regular air, because the nitrogen changes less than other types of gases, and it also doesn't escape quite as easily. So yeah, here we go. Pressure is defined, right? We talked about the pressure already, but let's look at the formula for that. It's defined as the force per unit area, right? How much force is exerted over a particular area? Now, we're going to go into detail on this when we hit the physics portion of our class next semester. But we just want you to see that that is the formula for it so far. We use Pascals to measure pressure. Now, you guys are probably familiar with the unit, which is like pounds per square inch, PSI, pounds per square inch. You also might be familiar with things like, what other one would you guys, atmospheres, maybe you guys have heard of atmospheres, you know, but in science we typically are going to use pascals, kilopascals, things like that, okay? So it is, a pascal is basically what 1 Newton force would be exerted over an area 1 meter squared. That's what's equal to 1 Pascal. Now the atmospheres, you guys have probably heard of, you know, 1 atmosphere of pressure. That's the amount of pressure that you'd have if the Earth, you know, the Earth's atmosphere was pushing down on you at sea level. That's kind of what that one is all about. All right, so let's talk then about buoyant force, because pressure has to do with particles. Buoyant force has to do a little bit with particles. What force makes a rubber duck float in a bathtub? Okay, why does a rubber duck stay floating? Well, every fluid exerts a buoyant force on matter. Okay, so in other words, kind of think about, here's the fluid, blue, 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 and if I put something on that fluid, blue, 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 if that, you know, thing stays up, that means the buoyant force is greater than the actual force of gravity that is pushing this thing down, right? And so all fluids are going to have some sort of buoyant force. If you have a greater amount of, you know, density and mass, then that thing might sink. And if the buoyant force is greater than the density and mass, then it's going to float, okay? So just know that buoyant force is this idea that all liquids or fluids, not just liquids, fluids, because gases are doing this too, right? All these fluids are putting a a force in an upward direction, okay, away from Earth. And again, a lot of this has to do with, density, if you think about that. For instance, a balloon that's floating in the air. Okay, why does it float in the air? Because the upward force, the upward buoyant force, is pushing it up. Okay, and ultimately, the density of the balloon is going to be less than the density of the air if it's going to continue to rise. If at any point the density of the balloon gets greater than the density of the air or that gas, that fluid, then it's going to sink, right? So that's the idea here. Now, Archimedes was the guy that kind of came up with this, and there's an interesting story where he was supposed to figure out, whether or not this guy that had made the crown had, cheated him and put something besides just gold in there. And so he did this experiment, and he was trying to figure out what the experiment was. And the legend goes that he was sitting in his bathtub, like he, got into this bathtub and noticed that the water level rose. And at that point he was like, oh, I know how to do this. I know how to figure out if this, king's crown is all gold or if it's got some other stuff in it. And so he jumped out of the tub and screamed Eureka and, ran naked through the streets, which sounds like really embarrassing. But remember, this is he was a Greek, scientist. And so back in those days, they had public baths. Their public baths were all visited in a naked form. So it wasn't as big of a deal as it sounds like, but yeah, it's still a pretty big deal, right? It's funny to at least think about it. Anyway, so he came up with this idea of buoyant force. Here's the concept. Like, let's say I have a little, like hole in my beaker, and my water level is filled right up to that beaker. As soon as I start putting this object into that beaker, then water is going to start flowing out, right? Because it's ready to start pouring out. If I collect this water, the weight of this water is exactly equal to the weight of that object that I put inside, okay? Their two masses are the same. Now, if I have an object that stays floating, okay, well, then, the buoyant force was greater than this, right? And so you can actually, and that's the way that, you can kind of look at ships that float in the sea. You can look at the buoyant force, the buoyant force is holding them up. If you were to compress the ship and not have any air inside and decrease its density, all that steel would just sink it to the bottom, right? So when the object is completely submerged, the weight of the displaced fluid is equal to the weight of the buoyant force acting on the object, okay? And in this case, this thing sinks, and so this, and I should actually clarify that a little bit, because if that actually sinks, then it could have a greater weight than that water. Okay, I apologize, I misstated that as I was talking about it. If it floats, its buoyant force will be equal to that weight of that object. But if it sinks, then the weight could be greater if it sinks. It's only if it floats is it going to be equal to the weight of the actual object. Anyway, cool stuff. All right, so let's continue on with the buoyant force. The object is going to float or sink based upon its density. If it's less dense, it'll float. If the object is more dense than fluid, it's going to sink. And here we again have our ship. And all of this space in here makes the overall density of this ship, okay, less dense than the water. And so that's why it floats, okay? If I took that same steel and I put it into a block form, it's going to sink. But because I've spread it out and I've shaped it into a hollow form, I increase the volume, and so I decrease the overall density, and so it stays floating, all right? Yeah, and so the buoyant force is able to hold it up. Now, there's something called Pascal's Principle, which is kind of cool. This is the way that brakes in your car work, and these really cool hydraulic lifts that they have in the car shops. Hydraulic meaning water, right? We deal with some water pressure here. Pascal's Principle states that a change in pressure at any point in an enclosed fluid will be transmitted equal to all parts of the fluid everywhere, even very, very, very far away. Okay, like the distance between where your foot is pushing on the brake pedal to the brakes, for instance, right? If the pressure in a container is increased at any point, the pressure increases at all points by the same amount. And this is cool because what this allows you to do is it lets you magnify forces. It's really awesome, okay? These hydraulic devices are based on Pascal's Principle. If I can apply a small force to a small little area, okay, and I have a little syringe that we can actually take a little syringe and push on the syringe and lift a person up. Okay, it's pretty cool. Same kind of thing here. If I push on this just a little bit, it has enough because you come over here and they make a bigger space over here. This is a greater area. And so the small area here is multiplied there. It's multiplied over and over and over again. So it amplifies the effects of that small little push on that small little area. And so it can lift up this car. Isn't that awesome? That's so cool. All right. And again, that's part of Pascal's principle. It's a neat thing. All right, fluids in motion. What affects the speed of a fluid in motion? Fluids move faster through small areas than they do through larger areas. If the overall flow rate remains constant, that's going to be true. Fluids also vary in the rate at which they flow. Now, this is something that has to do with Bernoulli's principle, okay? Let's talk about viscosity, and then we'll talk a little bit more about Bernoulli's principle. Our viscosity, if I have a very viscous substance, it's not going to flow very well. I think we mentioned in this class about that tar in New Zealand that they're filming and it like drops once every 12 years. Very, very viscous stuff, right? It's a resistance of a gas or a liquid to flow, okay? Liquids that are more viscous have molecules that have stronger attractions. So for instance, honey is more viscous than water, right? Honey is going to have a stronger attraction to itself than water has to itself. And so viscosity, you'll see a lot of times in oil for your car. You see, things like you've probably seen like 5W40 and 10W30 and things like that. Well, one of those numbers has to do with the viscosity. And you're going to want to have less viscous oil in the winter because you don't want your oil to get all gummy and to not let your engine move as well. So viscosity has to do with fluids in motion. Okay, the faster I can make it flow, the less attraction there is between those particles. All right, so Bernoulli's principle: fluid pressure decreases as speed increases. So again, this is one of those that they talk about, although there's been some discussion that I've seen. This isn't the best explanation, although at one point I was told that this was the best explanation for how airplanes fly. That if you have a wing, and the shape of the wing is kind of like this, and two particles of air that strike that, one goes up, one goes down, and again, talking about that rate being the same, if they both leave at the exact same time, then what happens is this one that had to go down, because that's a longer trip, is actually traveling faster. And you see that fluid pressure decreases as speed increases. And so that means that as this was going down here, that means the pressure, okay, was decreased on the bottom side of the wing. And this is what they say causes lift, because the pressure below is less, and then that causes the lift. Did I explain that right? I hope I did. Sounds all so wrong all of a sudden. But yeah, that's the idea behind Bernoulli's principle. And so you'll oftentimes see that as a part of why airplanes can fly. Okay, now let's talk about diffusion and thermal expansion. Two other concepts. Again, remember, all these things are talking about the kinetic theory, like how things are attracted to each other can describe viscosity, right? How those particles are flying over or below the wing, that can describe how an airplane flies, how particles are moving, right? All this kind of stuff is cool, right? A little Pascal's principle that particles are moving, from one side, the energy is transferred all to the other side. It's all sorts of cool stuff. Well, diffusion, spontaneous spreading of a gas or a liquid through the air, basically. Okay. Solid. I can't think of any diffusion examples that I've actually witnessed, but they do say that, for instance, particles of something that's solid are slowly leaving the air, leaving the substance and going into the air, so that for instance, naphthalene mothballs or carbon dioxide, dry ice, those things will diffuse because they're turning into gases. But anyway, perfume in a stilled room. If I talk about helium in a balloon is going at 1,200 meters per second, all right, compared to nitrogen, which is at 450 meters per second. And so if I were to talk about helium deflating faster than nitrogen, that would make sense. Smaller particles moving faster, finding little holes in that balloon, little tiny pores. The helium's going to be able to escape faster than the nitrogen, okay? And so the helium would deflate. Helium balloon would deflate faster than nitrogen, right? So diffusion is this idea that you can spread out spontaneously as particles are banging into each other and moving around. Thermal expansion, and that's when matter is heated, its volume is going to increase. And again, this is due to molecules moving faster. Kind of imagine like if you were all standing, you know, like in a dance party, right? You're all just like do, and everybody's like next to you, like, yeah, okay, grooving, yeah, that's nice. And then the music starts coming on, and it's a little crazy, right? And like boom, 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 and the beat drops. You're like, yeah, right? You're like going all over the place. All of a sudden, everybody's banging into each other. It's the same way that molecules are going. When those molecules are starting to bang into each other, people start to spread out, right? People are going to expand. That's what's happening when you have thermal expansion. This happens with solids. I don't know if you realize it, but a lot of bridges, if you'll take a close look at a lot of bridges, they're separate pieces. They're not even joined together. They have gaps. Like if you go down by, of course, they're tearing this stuff up here one of these days shortly. But if you go down by the dog food, Purina dog food plant, and you're along that part of I-70, and you're driving along, it's like boom, 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 boom. Well, if you actually look, each of those parts of that bridge are separate. They're not even connected. Not like really connected. There's like little pieces that might be around there, but not actually connected. And that's because of thermal expansion. They want to have a little bit of space between each of those sections so that concrete can expand, and then they can touch in the summer, but in the winter they're going to contract, and then they're going to be further apart. Okay. Another great example is, you know, we have these little things in here where you have a little ring that has to fit through a ball. And if you heat up that, you fit it through, and then you heat up that ball while it's on the other side of the ring, you can't pull it back out again, right? It's kind of cool. That's because that ball is getting expanded, and it's moving further and further apart. And again, this thermal expansion occurs in solids, liquids, and gases. It's a common thing. Okay, so that covers what we want to talk about today. You know, if you come into class after you've watched this and you're like, hey, I want to see that little ring and ball thing, Powers, ask me. It takes a little while to heat that thing up. I can't show it to you as a demo without taking quite a while, but I could definitely if you come into class and you want to see that, I would love to show it to you. You can heat it up for a while over there under a hot Bunsen burner and watch that thing go. Anyway, so did we figure out a little bit of applications to our kinetic theory? Yeah, we can now apply the kinetic theory to concepts of pressure, right? Particles are in constant motion. That's what causes pressure as the collision's occurring. Viscosity, attraction between particles. They're more attracted. It's going to be less, it's going to be more viscous the more attracted they are to each other, right? Diffusion. The whole reason that we have diffusion, the spreading out of gas particles, is because these things are in constant motion. Little particles are moving away. So we smell perfume, smell, oh, that pie smells wonderful, right? It's all little particles. You don't really, you realize that when you smell something, it's the particles are actually in your nose, they actually go and they attach to those little receptors inside your nose. And it's kind of disturbing when you think about this, because like when you smell a fart, that particle was actually inside somebody's butt just a little while ago, and now it's actually literally attached to part of your nose. Yeah, gross, right? Yeah, anyway, but cool at the same time. Okay, you now hate chemistry, and I was trying to get you to love it. No, you love it. Don't lie, you love it. All right, and then thermal expansion, right? The whole idea that things are moving apart, right? Rave, bah, bah, particles banging into each other, and they're going to spread out. Cool stuff, right? It's awesome stuff. You love it. Don't lie. You know you love it. God bless you. You have a great day.